Welcome back, everyone. So today we are going to be talking about the Pythagorean Theorem. This is something you've undoubtedly heard of, potentially even talked about in another class or even in first semester. So let's first start by defining the Pythagorean Theorem. Please fill in the blanks as we go. So a triangle is a right triangle if and only if the square of the hypotenuse is equal to the sum of the square of the legs. So this is just another way to write out the iconic a squared plus b squared equals c squared. So if we take this image here, we can see that c is a right angle given by this drawing in the corner. So if we were to take a squared, add that to b squared, we would be left with whatever value c squared is, as written out here. So some of you may have asked, what if a squared plus b squared doesn't equal c squared? So that's where we have the obtuse versus acute theorem. So again, fill in the blanks as we go. This one is for obtuse. If the square of the length of the longest side of a triangle is greater than the sum of the squares of the length of the other two sides, then the triangle is obtuse. So take this triangle here. If we were to add a squared and b squared together, and that were to happen to be less than c squared, we would know that angle C, which is opposite of side C, would be obtuse or greater than 90 degrees. Now conversely, if we take this definition again and say if the square of the length of the longest side of the triangle is less than the sum of the squares of the length of the other two sides, then the triangle is acute. So if we were to add a squared and b squared together, and that was greater than the value of c squared, we would be left with an acute triangle. All right, so we're going to do a little practice of finding the missing side length using the Pythagorean theorem. So we have our triangle here. Here is our right angle. So the side opposite that we'll call C. That'll be our hypotenuse. So we'll set it up a squared, or 4, plus b squared, or 8, equals c squared. So then 4 squared is 16, 8 squared is 64. We'll add those together. We'll get square root of 80. And if anybody remembers our simplifying radicals practice we did about a week ago, this is just one way to do it. There are multiple ways. Do whatever method you feel most comfortable with. But 2 divides 80 40 times, 2 divides 40 20 times, 2 divides 20 10 times, 2 divides 10 5 times. So now we have our prime factorization of 80. So we've got 4 2's and a 5. So we can either do two groups of 2 and be left with the square root of 4 times the square root of 4, which will give us 2 times 2, which will give us 4 again. Or we can just take the square root of 2 to the 4th, so square root of 16, which will give us 4. This 5 is all by its lonesome, so it's going to stay inside that radical. So C is going to equal 4 root 5. Let's get a new color for the next one. Going on to B, so we have 7 and 7 as our legs. So this is going to be an isosceles triangle because we have two side lengths of equal measure. And then we have our 90-degree angle here. So the side opposite that will be our hypotenuse. So we'll set up 7 squared plus 7 squared equals c squared. 7 squared is 49. And then 49 plus 49 is 98. So we take the radical of the square root of 98. So 2 divides 98 49 times, and 7 goes into 49 7 times. So we can pair these 7's together, get a perfect square number, and remove a 7 from the radical, and we're left with 2 inside. So 7 root 2 equals C. All right, moving on to C. So this time, if we go from the right angle to the hypotenuse, we know what the hypotenuse is. So now we're going to be looking for an unknown leg that we will call B. So we've got 6 and B equal, and then side length 10. So 6 squared plus B squared equals 10 squared. 6 squared is 36. 10 squared is 100. So if we subtract 36 from both sides, we get B squared equals 64. And if we take the square root of b squared, we're left with b. Square root of 64 is 8. Square root of 64 is also negative 8, but since this is the measurement of a side length, we can't have a negative measurement. All right. For D, the same thing is happening. We already know the hypotenuse, or the side opposite that right angle, as the root 45. So now we're looking for another leg. We're going to label that B. So we've got a 3 and a B, so 3 squared plus B squared is going to equal root 45 squared. So when we have root 45 squared, that means that we are taking the square root of 45 times the square root of 45. If we multiply those together, we're just going to be left with 45. So we have this give us 9. Sorry, I forgot to write a step here. So I took 9 from 3 squared, subtracted that from 45. We're left with B squared equals 36. And then if we take the square root of both B squared and 36, we get B equals 6. All right. Now let's talk about what kind of triangle we might have if we are given 3 side lengths. So our options are that the triangle is acute, right, obtuse, or not a possible triangle. And we'll talk about why it would be not possible in a minute. So acute and obtuse, that's going to be from that acute versus obtuse theorem from up here, and then a right triangle will be Pythagorean theorem. So let's just set it up to start with, we have our shortest legs and then our longest legs. So we'll do 2 squared plus 4 squared equals 5 squared. So 2 squared is 4, 4 squared is 16, 5 squared is 25. So if we add 4 and 16 together, we're going to get 20, and that is less than 5 squared, which is 25. So we know if the C length is longer than the sum of the other two, then that triangle will be obtuse. So now in this next one, we have 5 and 6 as the short legs, and then 13 as the longest leg. So now if you notice, this is, if we do 5 plus 6, we get 11. But there's a theorem we talked about earlier called the Triangle Inequality Theorem, which says that the other 2 side lengths of a triangle must add up to more than the third length. 5 plus 6 is 11. That is less than 13, so this triangle is not possible. Hence why we have not possible in the instructions. All right, we're going to keep on moving. So we've got 6 root 3 as our shorter lengths, and then 12. So we'll have 6 squared, 6 root 3 squared, and 12 squared. So 6 squared, that's going to give us 36. But now 6 root 3 squared. So when we have 6 root 3 squared, that means we're multiplying it by itself. So we'll multiply 6 by 6 and get 36, and then the root 3 by the root 3, and that's going to give us 3. So we're left with 36 times 3. So if we then multiply 36 times 3, we are going to get, one sec, let me confirm that number. We're going to get 108. So that's going to be 108 right there, equals 144. And if we add 108 and 36, we are left with 144. So a squared plus b squared equals c squared. That right there is a right triangle. All right. So now we have 11, 12, and 16. So 11 squared plus 12 squared equals 16 squared. So we get 121 plus 144 equals 256, 260. And if we add 121 to 144, we're going to get 265, which is greater than 256. So if the sum of a squared and b squared is greater than c squared, this triangle will be acute. All right, last one in this example. So we have 8, 8, and then 8 root 2. So same as always, 8 squared plus 8 squared equals 8 root 2 squared. So 8 squared is 64, so we have that twice. And then just like when we did 6 root 3 down here, when we have 8 root 2 squared, we're going to multiply it by itself. So the 8's multiply and we're left with 64. The root 2's multiply and we were left with 2. So then we have 64 times 2, which if we multiply that out, we'll get 128, and 64 plus 64 is 128. Therefore, we have another right triangle. All right, so we've got a couple word problems to go over. So if a square, let's get a new color real quick. So a square has a side length of 12 feet. So we know a square, all the side lengths are going to be equal. We want to figure out what is the length of the diagonal of that square. So if you can see right here, by adding that diagonal, we just turned that square into two triangles. And the short sides of the triangle are going to be 12. Squares always have right angles as the corners. So let's use the Pythagorean theorem. So a squared plus b squared, so those are both going to be 12s. And then c is going to be our hypotenuse, so c squared. 12 squared is 144, so we have that twice. And if we add 144 together, we get 288 equals c squared. Now we need to take the square root of both sides to get just c. And this was a little bit longer of a process, but 2 goes into 288 144 times, 2 goes into that 72 times, 2 goes into 72 36 times, 2 goes into 36 18 times, 2 goes into 18 9 times, 3 goes into 9 3 times. So now we have 1, 2, 3, 4, 5 2s and 2 3s. So we'll group together 4 of those and the 2 3s. So on the outside of our radical, we will have 4 times 3. Yikes, that was a little messy. Let's clean that up just a little bit. So we'll have 4 times 3, and then inside that singular 2 was left behind. So we'll have root 2. So 4 times 3, that's 12 root 2. So we are left with, that is a typo right there. The diagonal is going to be 12 root 2 equals c. All right, so we've got that right there. All right, so these dimensions are for Mrs. Provine's classroom. They are roughly accurate. So if we have a classroom that is 25 feet long and 30 feet wide, what is the distance from one corner of the room to the opposite corner? So we've got our right angle right here because it's a classroom, it's a rectangle. And then the side opposite will be C. So we set it up with Pythagorean Theorem. 25 squared plus 30 squared equals C squared. 25 squared is 625. 30 squared is 900. If we add those together, we get 1,525. And now we need to take the square root of both that and C squared. So over here we did that. So 1,525 is divisible by 5 305 times, which is divisible by 5 61 times. 61 is going to be a prime number in this situation. So we have a group of 5s, so that'll form a perfect square. And then we are left on the outside with 5 root 61 equals c. Okay, now we are going to have a new definition. We are going to be talking about what a Pythagorean triple is. And this is something we've been working with this entire class period. So please fill in the blanks as we go. So a Pythagorean triple, a set of 3 whole numbers that satisfy the Pythagorean theorem. But having whole numbers will come in handy later in a different part that we work on. But we also need to note that any multiple of a Pythagorean theorem is also a Pythagorean triple. So just an example of what that means. So 3, 4, 5, that's going to be one of the most iconic ones. If we do 3 squared plus 4 squared equals 5 squared, we get 9 plus 16 equals 25. 9 plus 16 is 25, so that will work as a Pythagorean triple. Now, if we were to multiply all of these side lengths by 2, we'd get 6, 8, and 10. This will also be a Pythagorean triple. We could multiply the side lengths by 10 and get 30, 40, and 50. Again, Pythagorean triples. This is an example of similar triangles, which is something we've talked about a ton. This is just scaling that triangle up by a factor of 2 or a factor of 10. You could scale it up by a factor of 1,000,000. It's still going to be a Pythagorean triple. All right, let's go on to 8, 15, and 17. So we have 8 squared plus 15 squared equals 17 squared. And if we do 8 times 8, that's going to be 64. And if we do 15 times 15, that's going to give us 225. If we add 64 to 225, we are left with 289, which is going to equal 289. And then there's another example. If we were to scale those side lengths up by a factor of 2, keeping that proportion constant, 16, 30, 34, again, this will work as a Pythagorean triple. All right, last thing we've got today. So we've got to find the third number in a Pythagorean triple. So let's start with, that is a 6. Let's start with this one. So we've got 12 and 16. For now, we'll just assume that those are the shortest lengths. So if we do 12 squared plus 16 squared, we'll have that equal to c squared. 12 squared is 144. 16 squared, 256. If we add those together, we get 400. And if we take the square root of 400 and c squared, we are left with 20 equals c. So our third dimension here will be 20. And if we were to look at these numbers and maybe divide them all by 4, we'd be left with, oh, look at that, 3, 4, and 5. So it's just scaled up by a factor of 4. All right, so let's go on to our next one. We're going to do the exact same thing. We've got 25 and 60. Again, we're just going to assume that they're the shortest lengths. So we've got 25 squared plus 60 squared equals c squared. 25 squared is going to be 625. 60 squared is 3600. If we add those two numbers together, we get 4,225. And if we take the square root of that, you're more than welcome to use a calculator. You get c equals 65. Okay, now this last one, again, we're just going to assume that these are the shortest lengths. So if we get 285 squared plus 293 squared equals c squared and add those together, we get 167074. If we take the square root of 167,074, we are not going to get a whole number. But notice that the definition for a Pythagorean triple says we need whole numbers. So let's try a different option. Let's say, well, we have 293, so let's maybe say that that's the hypotenuse or the longest side. So if we did 285 squared plus b squared, so we're looking for some unknown leg length now, equals 293, we take 285 squared and we subtract that from 293 squared, we get 4,624. That's going to equal b squared. So 293 squared is going to be 85,849, and then 285 squared is going to be 81,225. When we take the difference of those, b squared equals 4,624. Square root of both sides, we are left with b equals 68. So significantly shorter than the other two sides, but our Pythagorean triple is 68, 285, 293. Down here below is just a list of Pythagorean triples. Notice it says there are an infinite amount of them. That's true. This list goes on forever. These are some more iconic ones you're going to see, such as 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40, and 41. There's a bunch of them. This is just a useful tool that might help out on either your online assignment or preparing for your unit test.